Hello everyone. Welcome to chapter 2, the chemistry of life. This is a very important chapter. It is a long chapter. It has a lot of important information that you will be tested on, which is why I decided to make a video on it as well. All right, let's start. So these are my resources. These are the objectives. And let us get started. So there's a chemistry. So we are starting off with the elements of the body. In the periodic table, you see all of our elements. And on the periodic table, elements are arranged by their atomic number. And the atomic number is the number of protons in the nucleus. Elements are represented by 1 or 2 letter symbols. And 24 elements have biological roles. All right. So let's continue. So here we see an example of the element oxygen. The atomic number is 8, so it has 8 protons. Here we see helium, neon, and fluorine. All right. Let us continue. So what is a compound? A compound is a molecule composed of 2 or more different elements. For example, water or H2O is made up of the elements hydrogen and oxygen. We are going to focus on the important elements that the human body is made up of. So 6 major elements of the human body. Those are oxygen, O, carbon, C, hydrogen, H. Some of the lesser elements, we have nitrogen. We have other major ones, are nitrogen, calcium, and phosphorus. Nitrogen N, calcium Ca, phosphorus P. Some of the lesser elements are sulfur, potassium, which is K, sodium is Na, chlorine, magnesium, and iron. You need to know that if I mention the element O, it stands for oxygen. If I say Ca, it stands for calcium. H for hydrogen. K is for potassium. And Na is for sodium. We also have trace elements. These are present in minute amounts. Even though they're present in a very small amount in the human body, they are still very important for body functions. So those are, for example, chromium, cobalt, iodine, and selenium and fluorine. Short story, like I mentioned, the importance of knowing, for example, that K is potassium and Na is sodium. So my first language is Dutch. So I learned chemistry. In Dutch. And in Dutch, sodium is natrium. That's why it is Na for natrium. So when I was learning chemistry in English, I was looking for, everybody kept saying sodium. So on a periodic table, I was looking for SO and I could not find SO. After a day or two, I realized that it is sodium is Na. So don't be like me. Know the symbols of these major elements. All right? For the major and the lesser elements. So again, here we see the elements of the human body. We have oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. I like this image I found on Google. It also shows you how much water we are made up of, the minerals, fats, how much fat make up our body, and the other lesser elements. We have minerals. What are minerals? Minerals are inorganic elements extracted from soil by plants. So how do we get those elements into our body? By ingesting the foods rich in elements. For example, calcium and phosphorus. Why are these two inorganic elements important? They make up our bones. They make up our teeth, for example. These minerals are also important for enzyme functions. And so yes, let's continue. Atoms. So from the hierarchy of complexity from chapter 1, you learned how we went from organism to organ system to organs to tissues to cells to macromolecules, molecules, all the way down to our atoms. And an atom is the basic unit of matter. It comes from the word atomos, which means unable to cut. And an atom consists of a proton, which is a positive charge, a neutron, which has no charge, and electrons would have a negative charge. The atomic mass, remember our atomic mass from the earlier slide? The atomic mass is approximately equal to the total number of protons and neutrons. Where do we find those protons? Where do we find those protons and the neutrons? In the nucleus. So here we see an example of the structure of an atom. In the nucleus, we find neutrons, which have no charge, and protons, which have a positive charge. And the electrons orbit around the nucleus. So the electrons orbit around the nucleus in an electron cloud. The electrons of the outermost shell, those are called valence electrons. And those valence electrons determine the chemical bonding properties of an atom. All right? So in this illustration, we see it, the electrons are very close to the nucleus. But in reality, these distances can be very, very, very large. All right? Isotopes. So isotopes are varieties of an element that differ only in the number of neutrons. Where do we find our neutrons again? In the nucleus. What else do we find in the nucleus? Protons. So if we have a different number of neutrons, you will therefore also have a different atomic weight, because atomic weight depends on neutrons and protons. So here we have the isotopes of hydrogen. Hydrogen here we see it has one proton, no neutrons, and one electron. Wonderful. Another isotope of hydrogen is deuterium. Deuterium has one proton, one neutron, and one electron orbiting the nucleus. Since we have the addition of a neutron, here the atomic weight is 2, versus the atomic weight of hydrogen would be 1. And here we have tritium, another isotope of hydrogen, where we have our proton and 2 neutrons and 1 orbiting electron. So the atomic weight here would be 1 plus 1 plus 1, which is 3. So that is what an isotope is. Do you need to know what an isotope is? Yes. So here we have some special isotopes. Isotopes and radioactivity. So our isotopes, they differ in neutron number. Many of our isotopes, they are unstable and they decay, which means they break down to more stable isotopes. And when they break down, they give off radiation. All right? So unstable isotopes are therefore called radioisotopes. And the process in which they decay, so the process in which they break down, is called radioactivity. Every element has at least one radioisotope. Has radioisotopes. So high energy radiation, such as that emitted by radioisotopes, what happens is they eject electrons from other atoms, converting those atoms to ions. That is why it is called ionizing radiation. Some examples of ionizing radiation is our ultraviolet rays. They're also called our X-rays. And 3 kinds of radiations produced by nuclear decay. That is, those are alpha particles, beta particles, and gamma rays. An alpha particle consists of 2 protons and 2 neutrons. And a beta particle is a free electron. So why is this important? Because in high doses, ionizing radiation is quickly fatal. But in lower doses, it can be mutagenic. What does that mean? It can cause mutations in DNA. They can also be carcinogenic, which means it can trigger cancer because of those mutations. This is an example of why X-rays are contraindicated during pregnancy. This is also why, for examples, we need to limit the exposure to X-rays. So yes, and this is Dr. Marie Curie. This was her portrait in 1911. This is the first woman to receive a Nobel Prize and the first woman in the world to receive a PhD. She came up with the term radioactivity, and she discovered the radioactivity of polonium and radium. Because of her discovery, now we have X-rays and other imaging techniques because of her discovery. But again, because of all her exposure to all of these ionizing radiations, she died of radiation poisoning at the age of 67. So here we have another important table. Like I mentioned, I love tables. These tables, I like studying from them because after you go through these slides, you can just put a large box over this right side and see if you can come up with a term of, hey, what is ionization? What is an ion? What is an anion? So that is how I recommend you study while using these tables. Ionization is the transfer of electrons from one atom to another. What is an ion? This is a charged particle, which means it has unequal number of protons and electrons. Ions with opposite charges are attracted to each other. Think of a magnet. So if they're attracted to each other. An anion is a particle that has a net negative charge because it gained electrons. A cation is a particle that has a net positive charge because it lost electrons. So here we have a neutral atom. When it loses electrons, it loses negativity. It becomes a cation with a positive charge. And here we have another neutral atom. It gains electrons. Now it is an anion with a net negative charge. Salts such as sodium chloride and calcium chloride are electrically neutral compounds of cations plus anions. So those are salts. In most cases, when it comes to human physiology, they easily dissociate in water to give us electrolytes. So if you put sodium chloride in water, it will give you sodium and chloride. Which are those electrolytes? Water electrolytes, substances that ionize in water and form solutions capable of conducting electric currents because they have positive and negative charges. So here we have an example of, here we have sodium. It has one valence electron here. Chlorine with its valence electrons there. The transfer of an electron from sodium to chloride, that now gives us sodium chloride. We lost an electron there, so it is positive. We gained the electron here, so it is negative. So this is a charged sodium ion and a chloride ion that then results. This is ionization. And here we have the electrolytes that will be produced when we place these salts in water. Calcium will give us calcium chloride. Sodium will give us sodium chloride. Sodium bicarbonate will give us sodium and bicarbonate, etc., etc. Again, electrolytes are salts that ionize in water and form solutions capable of conducting an electric current. You will see many examples throughout this semester where we take a look at these electrical currents in nerves because of the different electrolytes, electrical currents in muscle tissue because of the different electrolytes. And electrolytes, they are measured in equivalents or milliequivalents per liter. Free radicals. So free radicals are short-lived particles with an unusual number of electrons. They are produced by normal metabolic reactions, radiation, and certain chemicals. So right now, your body is doing metabolism. We are making energy, we're using energy. In this normal healthy process that our body does constantly, we are also producing free radicals. Free radicals, they can trigger reactions that destroy molecules and can cause cancer, death of heart tissue, and aging. It is thought that the part of a process of aging is because of these free radicals. So here we have a normal oxygen. Now this is one is an oxygen free radical because now we have an unpaired electron. And often our free radicals, they're denoted as an O2 and then a negative, an unpaired free radicals. So how, if we naturally produce free radicals, how come we don't just constantly, how does our body get rid of those free radicals? Through antioxidants. Antioxidants are chemicals that neutralize free radicals. An example of such an antioxidant is superoxide dismutase. So here we are generating free radicals. What SOD or superoxide dismutase does, it takes hydrogen and generates hydrogen peroxide. Hydrogen peroxide then, also because of superoxide dismutase or catalase, we convert something that is destructive to the body, and we convert it into water. Water is everywhere. We need water. So we are able to take something that is harmful and make simple water. Other examples of antioxidants are selenium, vitamin E, vitamin C, carotenoids. So that's why we need have a variety in our diet, so we can get antioxidants into our system. So now when you go to the supermarket and you see rich in antioxidants, now you know why you need those antioxidants. All right. Some more definitions. So some more general chemistry. So a molecule is a particle composed of two or more atoms united by a chemical bond. A compound is a molecule composed of two or more different elements like H2O, water. The molecular formula, it identifies the constituents, elements, and how many atoms of each are present. We'll see that in a second. Structural formula, it identifies the location of each atom. And then isomers, these are molecules with identical molecular formula but different arrangements of atoms. We're going to go into detail on these last three terms. So let's start. So say we're looking at C6H12O6. This is glucose. The molecular weight of glucose is 180 AMU. So why are we looking at that? So glucose, C6H12O6. What we are reading over there, C6H12O6, that is the molecular formula of glucose. Here again we have ethanol and ethyl ether. The molecular formula of ethanol and ethyl ether is C2H6O. They have the same molecular formula, but they have a different structural formula. How they are arranged in space is different. Here we have a hydroxyl group, and here we have a carbon, an oxygen, and then another carbon. So same molecular formula, but different arrangement of our atoms, different structural formula. That is what makes ethanol and ethyl ether isomers of each other. They have the same molecular formula, but different structural formula. All right, we need to know what an isomer is. Let's now go through some of our chemical bonds. So chemical bonds, they hold atoms together within a molecule or attract one molecule to another. We have different types of chemical bonds. We have ionic bonds, covalent bonds, hydrogen bonds, and van der Waals forces. An ionic bond is an attraction of a cation to an anion. Which example did we see a couple of times already of an ionic bond? A bond between an attraction between a cation and an anion. That is, hopefully we're all yelling, sodium chloride. And again, ionic bonds are easily broken by water, and when it does so, it gives us those electrolytes. Okay, next we have covalent bonds. A covalent bond is where atoms, they don't attract, but they share one or more pairs of electrons. If we say there is a single covalent bond, which means we're sharing one pair of electrons. If there is a double covalent bond, we are sharing two pairs. If there is a triple covalent bond, we're sharing three pairs of electrons. And then sometimes those electrons that are shared, they might not be shared equally. When they are shared equally, that means that that is a non-polar covalent bond. But when the electrons are not shared equally, some electrons are more towards one side of the bond than the other, then it is a polar covalent bond. So here, for example, the electrons are shared equally. So the electrons are shared equally. This is a non-polar covalent bond. But here we see the electrons are more towards the oxygen than the hydrogen. This therefore is a polar covalent bond. We then say that the oxygen in this bond is slightly negative and the hydrogen is slightly positive. It's still a covalent bond, but electrons are just not shared equally. We also have van der Waals forces. These are weak, brief attractions between neutral atoms. Because of the electron cloud density, as those electrons are orbiting around the nucleus, at some point in time, some electrons might be more towards one side and more towards one side than the other, creating also a difference in charge in the other atom, and this will create a very weak, brief attraction between neutral atoms. All right, here's a wonderful table from the book. I highly recommend going through it because it shows you the bond type, definition, and the different remarks. Awesome. Then we have our amazing hydrogen bonds. Hydrogen bonds are weak attractions between a slightly positive hydrogen atom in one molecule and a slightly negative oxygen or nitrogen in another atom. So here we see a water molecule here, water molecule, water molecule, water molecule. Between this oxygen and hydrogen and this oxygen and this hydrogen, we have a solid line to represent a covalent bond. And again, we're also able to see that the electron cloud is not equally distributed. So this is therefore a polar covalent bond. But we also see that we have a weak attraction between the oxygen in one water molecule and a hydrogen or a nitrogen in another molecule. And this stippled line represents a hydrogen bond. So we see a hydrogen bond here, hydrogen bond here, here, and then there. Therefore, we can say when it comes to our water molecules, in the water molecule itself, between oxygen and hydrogen, we have a solid line of covalent bonds, but between water molecules, we have those hydrogen bonds. These hydrogen bonds are extremely important. For example, it is what holds our DNA together. These weak attractions, they might be weak by themselves, but when they work together, they're very strong and very important bonds. So large molecules like DNA and proteins are shaped in part by the formation of hydrogen bonds within them. All right, you need to know covalent bond versus hydrogen bonds. And because of those hydrogen bonds, and because of the unique shape of water has special properties. So the polar covalent bonds and the V-shaped molecule gives water a set of properties. We have the properties of solvency, cohesion, adhesion, chemical reactivity, and thermal stability. And we're going to go through all of them. Starting off with solvency, we know water is a universal solvent. We know this. We're just now adding a definition to something we already knew. We know that we can use water to dissolve many different things. So water is called a universal solvent. Water, when water, we also know that water can break down ionic bonds, and when it does so, we create hydration spheres. So we place salt in water, it will give us these electrolytes, sodium and chloride. Sodium has a positive charge, therefore the negative part of water will be facing the sodium, versus here the negative chloride will be surrounded by the positive charge, the slightly positive faces, the slightly positive poles of water. All right, so these are hydration spheres. Other properties of water: adhesion. So adhesion is the attraction among molecules of different substances. So water molecules stick to other things. This is why there is an upward curve when you take a look at water in a test tube. This is also how water is able to go from the roots to the leaves, because of the adhesive properties of water. Because water molecules likes to stick to things. That is adhesion. We then have cohesion. Cohesion is attraction among molecules of the same substance. Makes water molecules stick to each other. This produces a surface tension, makes kind of a skin on water. So with this cohesion, I'd like to give the example of you are playing. Let's make a scenario. So now you have a scenario. You're a kid and you're playing. Instead of folding the sheets, you're playing with the sheets. And now you're all holding a corner of a bed sheet. All right, can we all picture this? We're holding the corner of a bed sheet. If you're holding the corner of the bed sheet very tightly, you are creating a surface tension. You're creating surface tension. If you place a ball in the center of that sheet, that ball will be able to stand up. You can bounce the ball up and down. It will not just sink through the sheet. So that is surface tension. So because of these cohesive properties of water, we are creating a surface tension. So it makes kind of a skin underwater. That's why certain bugs are able to kind of glide and stand underwater. And then we also have chemical reactivity, like you saw a second ago, which is the ability of water to be involved in different reactions, like breaking down ionic bonds. Water, because of water, we also have specific properties of water, like hydrophilic versus hydrophobic. Hydrophilic means substances that are able to dissolve in water. So hydrophilic substances, they literally love water. Think of anything that is polarized or charged, that is usually hydrophilic. So that is salts and ions, and also sugar. Yes, good examples. First is hydrophobic, that is hydro or water hating. These substances do not dissolve in water. Hydrophobic substances, think of non-polar substances like oil or fats. Also, neutral substances are hydrophobic. Yes, so think of oils and fats. Alright, so next we have a mixture versus a compound. So your book goes through a compound. Think of, again, table salt, sodium plus chloride. Sodium by itself, very dangerous. Chloride by itself, very dangerous. Together, lovely, tasty table salt. That is a compound. Next, we have a mixture, salt and mango. Salt plus mango will give you salt and mango. Sodium and chloride will give you table salt, something completely different. That is a compound. But a mixture, salt plus mango, will give you salt and mango. Mango tastes sweet, so when you take a bite out of it, mango will still stay sweet, but you also taste the salt with each bite. You will taste the mixture of salt and mango. You're not going to taste a completely new compound. You are tasting a mixture of the two. And we have different types of mixtures, solutions, suspensions, and colloids. Colloid solutions, emulsions, and suspension. So let's jump right to this table from the book. It shows you a solution. The particles are less than 1 nanometers, colloids 1 to 100, and suspensions greater than 100. The appearance, solutions are clear in appearance, colloids are often cloudy, and suspensions are cloudy to opaque. Will the particles settle? They will not settle unless it is a suspension. Suspensions, the particles can settle. They do settle. Will particles pass through a selectively permeable membrane in a solution? Yes, they will pass, but in colloids and suspensions, they will not. Some examples of solutions are glucose in blood, oxygen in water, and saline solutions and sugar in coffee. These are examples of solutions. Examples of colloids: proteins in blood, intracellular fluid, milk protein, and gelatin. They're often cloudy in appearance. They do not settle, and they do not pass through a selectively permeable membrane. Often it's because they are too large, because they are 1 to 100 nanometers in size. And then suspensions. Examples are our blood cells in our blood plasma. If you take someone's blood and let it sit, it will separate into different layers. Cornstarch in water, fats in blood, and kaopectate. And then, yes, different measures of concentrations. You need to, I'm not going to test you on this specifically, but if you read, for example, 5% sucrose by weight and volume, you should know what that means. It is a measure of a concentration. If you read, for example, 1 molar, 1 milli equivalent per liter of this, know that it represents a concentration. All right. So when you're reviewing, please go through this slide and know that these are different measures of concentrations. An important concentration you should be familiar with is molarity. So molarity is 1 mole of a chemical is the number of grams equal to its molecular weight. Molarity, capital M, is a measure of the number of moles of a solute per liter. Moles per liter, that is molarity. This reflects not merely the weight of the solute in the solution, but the number of molecules per volume. Alright, so molarity is a measurement unit that tells us about the concentrations of a solution. Here we have 0.25 molar, 0.50 molar, and 1 molar. Do you notice that in each of them, there is more solutes, more moles in that liter of solution. Alright? So it is a measure of concentration. Acids, bases, and pH. What is an acid? An acid is a proton donor. What is a base? A base is a proton acceptor. pH is a measure of the acidity derived from the molarity. Here's that term again. Alright, so pH is the measure of acidity derived from the molarity of hydrogen ions. So the pH of 7 is said to be the neutral pH. When you have a pH less than 7.35, we're said to be acidic. If it's greater than 7.45, we say that solution is basic. So it is determined by the hydrogen ion concentration, because basically it is your proton concentration. So for example, if something has a pH, how do you calculate the pH? It's a negative log of the hydrogen ion concentration. So if your hydrogen ion concentration is 10 to the negative 3, that pH is 3. So the pH of 4, so a change of 1 number on the pH scale represents a 10-fold change in hydrogen ion concentration. So the pH of 4 is 10 times as acidic than the pH of 5. So I like this representation. It's more easier to understand with this representation here. So in this image, we see our pH scale, which goes from 0 to 14. When I have a pH of 0, we have a hydrogen ion concentration of 1. The pH is a negative log of 1, which will be 0. Negative log of 0.1 is 1. Negative log of 0.01 is 2. So as the hydrogen ion concentration decreases, your pH increases. Therefore, we can also say The more hydrogen ions you have, the more acidic. The less hydrogen ions you have, the more alkaline. The more hydrogen ions you have, the more you can donate hydrogen ions, which makes you an acid. The less hydrogen ions you have, the less likely you can donate the hydrogen ion, which makes you a base or more alkaline. All right? So from 0 to 14, acidic to alkaline or basic, a pH of 7 is said to be neutral. An example of that is pure water. With this image from the book, you're able to see a lovely pH scale. 0 from 7, anything less than 7, we are increasing in the acidity. From 7 towards 40, we're increasingly becoming more, we are becoming more basic. All right, did you know that milk was acidic? I didn't know that. I think that's interesting. Bread, also acidic. Bananas, also acidic. Did you know that? I did know that coffee is acidic because it has an effect on your teeth. Wine and vinegar, also acidic. Of course, we know that lemon juice is also acidic. And then again, your gastric juices, your enzymes, all your contents of your stomach, it is very acidic. Isn't that fascinating that what is inside of our stomach right now can have acidity of 0.9 to 3. So basically, if you place a metal spoon in your stomach, it would dissolve. A question for you. How come right now this acidity is not eating away at your stomach lining? Think about that and come to me with the answer. All right? Okay, so our body, why do we need to know acids and bases? So the importance of acids and bases in the human body. A very slight disturbance of pH can disrupt physiological functions. It can also alter drug actions. We just mentioned one change in pH from just 6 to 7 means it is a 10-fold difference in hydrogen ion concentrations. So our body's pH should be between 7.35 and 7.45. Anything outside of that range will give you symptoms. Now you have a condition that we need to fix. How does our body try to maintain this very narrow pH range? Our body uses buffers. And our body has physiological buffers, which is the respiratory system and the urinary system. So we're going to learn about that in much more detail when we go through the renal chapter. Some symptoms of acid-base imbalances are tremors, fainting, paralysis, and even death. I remember during my rotations, one of the first places where I saw measurements of pH, measurements of pH was in the ICU. Because if you're in the ICU, you are very sick. So we need to know everything about your body system. So we also get your arterial blood gas measurements where they give you your pH reading as well. All right, a little bit of physics. Energy. Energy is the capacity to do work. To do work means to move something. All body activities are forms of work. Right now, as I'm speaking, I am working, literally and also physiologically. All right, for me to just produce speech, for me to be able to be awake, my cells, everything is using energy. It's the capacity to do work. There's also something called potential energy. This is the energy stored in an object but not currently doing any work. Think of water behind a dam. So area A. Area A in this image, it has a lot of potential energy. Energy is just sitting there. It's not moving right now, but it can. Then we have B, kinetic energy. This is energy of motion. It is doing work. The example again of water flowing through a dam generating electricity. We also have free energy. This is the potential energy available in a system to do useful work. In human physiology, the most relevant free energy is the energy stored in chemical bonds. So we're going to learn about this again in a lot of detail, how much energy is stored in our energy bonds, especially in those bonds in our ATP, adenosine triphosphate. Some of our reactions in the body, they can be exergonic and they can be endergonic. Exergonic reactions are energy releasing reactions. They're also called spontaneous reactions, and they can occur without energy. Endergonic reactions, these are energy absorbing reactions, for example, photosynthesis. All chemical reactions in the body are collectively called metabolism. So if I were to ask you tomorrow, I wake you up at midnight, what is metabolism? All the chemical reactions in the body are called metabolism. All right? So in these next couple of slides, we're going to go through energy transfer reactions. Some of them are exergonic and some of them are endergonic. They can occur without energy and they need energy to be able to occur. All right. Let's go through some chemical reactions. First off, we have different classes of them: decomposition and synthesis, anabolism and catabolism, oxidation and reduction, and they also have exchange reactions. Decomposition reactions, this is where large molecules are broken down into two or more smaller ones. So we take a large molecules, AB, we're breaking it down into A and B. Think of when something is decomposing, it is breaking down into smaller components. We have synthesis reactions where two or more smaller molecules combine to form a larger one. So it's basically the opposite of decomposition. We're taking small a and small b, making a larger AB. And then we also have exchange reactions. It's where two molecules, so two molecules exchange atoms or groups of atoms. That's exchange reactions. So we have AB plus CD giving us ABCD, and the exchange here we have AC plus BD. So let's take a look at what we just read. So we are taking a large molecule, breaking it down into smaller ones. This therefore would be a decomposition reactions. So if I give you an image like this, know what I am describing. We also are able to see we're taking smaller molecules, combining them to give us one large one. This is a synthesis reactions. And here we see AB plus CD, an intermediate molecule, and then we have AC and BD. This is an example of an exchange reaction. We also have a reversible reaction. These reversible reactions, they are very important and they're very prevalent throughout the human body. Here we have a reversible reaction that by the end of Anatomy and Physiology 1 and 2, you will know by heart. We take CO2, carbon dioxide, and water. We will give us carbonic acid, which will then give us bicarbonate and hydrogen ion. This is a reversible reaction because it can go in either direction. And this first reaction is catalyzed by the enzyme carbonic anhydrase. If there is no carbonic anhydrase, this first step cannot occur. All right? Is there carbonic anhydrase here? No. Only in that step. And this again is a reversible reaction. That's why it has a double arrow, so it can occur in either direction. So when we get to the respiratory system, urinary system, and digestive system, you will go through this equation over and over and over again. Let's go now through metabolism again, but we're going to go through the different types of reactions involved in metabolism. So if I say this chemical is undergoing an anabolic reaction, you need to know what anabolism is. Anabolism is energy storing synthesis reactions. So since it requires energy, it is therefore an endergonic reaction. Catabolism is an energy releasing decomposition reaction. So we are taking something large and catabolizing it. We're breaking it down. We're breaking down the covalent bonds to produce smaller molecules. Therefore, since we're breaking these bonds, it is an energy releasing reaction or an exergonic reaction. If you hold a beaker of water in your hand and pour sulfuric acid into it, the beaker will get so hot you may have to put it down because it is releasing energy. If you break down energy storage molecules to run a race, you will too get hot. Same concepts. Both reactions are exergonic reactions. All right? We also have reduction reactions and oxidation reactions. Reduction is a chemical reaction in which a molecule gains electrons and therefore it also gains energy. When a molecule accepts electrons, it is said to be reduced. So reduction is gain of electrons. A molecule that donates electrons to another is therefore called a reducing agent. All right, an electron donor. And often in reactions, the electrons that are transferred are in the form of hydrogen ions. Oxidation is any chemical reaction in which a molecule gives up electrons and releases energy. A molecule is oxidized by this process, and whatever molecule takes those electrons is the oxidizing agent, which is the electron acceptor. And quite often, when it comes to oxidation reactions, oxygen has been added to a molecule, so often it's in the form of oxygen. So here, with this mnemonic, the mnemonic you can use is oil rig. Oxidation is loss of electrons and reduction is gain of electrons. An example of an oxidation reaction is the rusting of iron. So this is a slow oxidation process in which iron, oxygen, and water gives you rust, iron oxide. So iron here is oxidized and then oxygen is reduced. Oxidation, it loses an electron. Reduction, here it gains an electron. And like we mentioned, when we see, here we see the reduction is gaining an electron, and often it's in the form of hydrogen atoms. All right, so oxidation, reduction. Oxidation is loss, reduction is gain. So these reactions, reduction and oxidation reactions, together we call them redox reactions. We can symbolize oxidation and reduction as follows, letting A and B symbolize arbitrary molecules and E represent the electrons being transferred. So here we see A with its electrons and B, this is the reduced state because here it has an extra electron, so it gained it. You have a low energy oxidized state. When A and the electron here becomes A, now it has been oxidized. Where here B, we gain an electron, so now it has been reduced. So these electrons on A are transferred to B. Here we have B. Here the electrons here are transferred to B. So oxidation is release of electrons. Reduction is accepting or gaining those electrons. All right. So whenever you see reactions where electrons are lost, oxidations, hydrogen is lost, oxidation, oxygen is gained, oxidation. Electrons are gained, reduction, hydrogen is gained, reduction, oxygen is lost, that is a reduction reaction. All right. Chemical reactions, some more. What factors affect chemical reactions? You know this. We're just going to give some definitions to some concepts you are already familiar with. I like to give the example of tea because I like tea. If you're making tea right now and the water is cold, it will take a very long time for that water to become tea because what is actually happening when you're making tea, all of those molecules are not moving as much because the water is cold. Now, if you now heat up that water, the molecules now are moving more violently. Now you're going to be able to make tea much more quickly. So chemical reactions are based on molecular motion and collisions. Collisions with enough force and correct orientations, they break or form bonds. The rate of a reaction depends on the nature of the reactants, the frequency, and the force of those collisions. If you increase the concentration of the reactants, there's going to be more collisions, increasing the rate of the reactions. We're going to get to our results much faster. Increasing the temperature, more collisions, get to our goal much faster. What if you don't have a concentration of reactants and you don't have temperature? What else can we add to get to our goal much more quickly? Catalyst. A catalyst is an enzyme catalyst. It will bind to the reactant, hold them in the correct orientation, and those catalysts, they just hold it in place, let the reaction occur more quickly, and they themselves are not used up. The catalysts are not changed. And the most important biological catalyst in our body, those are our enzymes. We saw an enzyme earlier with CO2 and water giving us carbonic anhydrase. Giving us carbonic acid, and that enzyme was carbonic anhydrase. Sorry. Yes. Hello, class. Today we are going to continue chapter 2, and we're going to start on organic chemistry. So we're going to have about 30 slides covering organic chemistry. For those of you who know about organic chemistry, you know that is way too little slides. So we're going to go over the basics, all right? So starting off with our first slide. Organic chemistry is the study of compounds containing carbon. So here we see carbon, containing carbon. There are 4 categories of carbon compounds. We have carbohydrates, lipids, proteins, and nucleic acids. Why is carbon so unique? It is because carbon has 4 valence electrons. And those valence electrons means that carbon can form 4 covalent bonds with other atoms. The carbon atoms bind readily with one another to form carbon backbones. So you will see in the next couple of slides a lot of long carbon backbones, and attached to these carbon backbones you will have bonds with hydrogen, oxygen, nitrogen, sulfur, and other elements. You will also be learning about functional groups. What is a functional group? It is a small cluster of atoms attached to a carbon backbone, and the functional group determines the properties of different organic molecules. So let's take a look at some of these functional groups. First off, we have hydroxyl. Hydroxyl is OH, and if a carbon backbone has an OH at the end of it, it means it is either a sugar or an alcohol. If you see CH3, it means that it's a methyl group, and methyl groups occur in fats, oils, steroids, and amino acids. Next, we have carboxyl, which is COOH. COOH means we have a carbon with a double bond to oxygen and a carbon bound to a hydroxyl, so O and then a H. And where do we find carboxyl functional groups? Amino acids, sugars, and proteins. Next, we have amino, where we have a nitrogen, a hydrogen, and a hydrogen, and this occurs also in amino acids and proteins. And next, we have phosphate, H2PO4. So here we have a phosphorus and oxygen, 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 oxygen. And here we see a triple bond, so this is a phosphate group. It's often denoted by just a line and then a P in a circle. All right. So Monomers and polymers. So when it comes to organic chemistry, we're going to see a lot of monomers and polymers. And again, you already know this. For example, the monomer, amino acids, and the polymer would be our proteins. All right. So we have macromolecules. Macromolecules are very large organic molecules with high molecular weights. What are polymers? Macromolecules made of repetitive series of identical or similar subunits. For example, starch is a polymer of about 3,000 glucose monomers. And what is polymerization? This is when we join monomers together to form a polymer. And often when we are forming polymers, it involves these reactions. First, let's go through a dehydration synthesis reaction, also called a condensation reaction. This is where the monomers conveniently bind together to form a polymer. And a hydroxyl group is removed from one monomer and a hydrogen is removed from another. Therefore, we're going to form, hopefully you know, OH and H, we're going to form water as a byproduct. That's why it's called dehydration. We will have water as a byproduct. Next, we have hydrolysis. Hydrolysis is the opposite of a dehydration synthesis reaction. This is where we are splitting a polymer into its monomers, and this requires water. An enzyme helps break down the covalent bond that links the two monomers together, releasing hydroxyl and hydrogen and a proton, so releasing water. So let's take a look at what that looks like. So here we see dehydration synthesis reaction. What is this functional group? Hopefully we're all saying hydroxyl. What is this one? Also hydroxyl. So here we have monomer 1 and monomer 2 coming together to give us a dimer. And this dimer was able to form this bond, this covalent bond here, and also water as a byproduct. Next, we have the opposite, the hydrolysis reaction. In this hydrolysis reaction, we're going to try and break this covalent bond, and that requires the addition of water. So we are consuming water to give us two monomers. Each will have then a hydroxyl functional group as well. All right, please know these two reactions. Next, we're going to go through our 4 types and the different functions of our major organic molecules, starting off with our carbohydrates. Our carbohydrates are hydrophilic organic molecules. What does that again? Do they like water or do they hate water? Are they hydrophilic or hydrophobic? Hopefully, we're all yelling at the screen they are hydrophilic. And some examples of carbohydrates are sugars and starches. The sugar and starches, these carbohydrates, they have a general formula of CH2O and N. And then the N tells you the number of carbons. So if the number of carbons is 6, you will have C6H12O6. And when it comes to the naming of your carbohydrates, it often has the root word saccharine and the suffix "-ose". So we're gonna see that in a bunch of examples in the next couple of slides. The simplest form of carbohydrates we have, those are our monosaccharides. Those are the monomers. And we have 3 important monomers. We have glucose, galactose, and fructose. All of these 3 have the molecular formula C6H12O6. An example, and glucose is what is actually our blood sugar. So from what we have learned in chapter 2, we have C6H12O6, which is the same molecular formula for glucose, galactose, and fructose. Therefore, glucose, galactose, and fructose are what of each other? We're all yelling isomers. They're all isomers of each other. Same molecular formula, different structural formula. Yes, glucose, galactose, and fructose. So here we have those 3 major monosaccharides. I do not expect you to be able to draw these out, but I do want you to know that they all have the same molecular formula: glucose, galactose, and fructose. when you have monosaccharide plus monosaccharide, you therefore get disaccharides. So disaccharides are sugars made up of two covalently bonded monosaccharides, and there are three major disaccharides you need to be very familiar with. Those are sucrose, lactose, and maltose. They all consist of two monosaccharides joined through an oxygen atom. So let's look at sucrose. What is sucrose? It's stable sugar, and that is literally glucose plus fructose. Then we have lactose. What is lactose? It is glucose plus galactose. And then we have maltose, which is glucose plus glucose. So if you have a multiple choice question and I were to ask you, the disaccharides lactose is made up of glucose and you will pick galactose. The disaccharide sucrose is made up of glucose and fructose, and maltose is made up of glucose and glucose. All right, we need to know these disaccharides. This is a lovely table from your book. It goes through the different types of carbohydrates, the monosaccharides, those disaccharides. It also goes through several polysaccharides and some conjugated carbohydrates. Some polysaccharides we have noted here are cellulose. This is dietary fiber. Starch is the energy storage in plant cells and is the energy source in our human diet. And glycogen is the energy storage in animal cells. So it's how we store glucose by forming glycogen. And then we have conjugated carbohydrates like glycoprotein, glycolipid, and proteoglycans. Know what those are. Lovely table for you to study from. So that was that. Now we're going to go through our lipids. Lipids are hydrophobic molecules with a high ratio of hydrogen to oxygen. More calories per gram than the carbohydrates, and our 5 primary types of lipids we have are fatty acids, triglycerides, phospholipids, eicosanoids, and steroids. Let's start off with our fatty acids. So a fatty acid has a 4 to 24 carbon chain with a carboxyl group, hopefully we know what functional group that is, and a methyl group at the end. And fatty acids are categorized as either being saturated or unsaturated. Saturated means it has no double bonds between the carbon atoms. Unsaturated, it has one or more double bonds in a carbon chain. Polyunsaturated fatty acids have multiple double bonds in their carbon chain. All right, so that's what we need to know that. So here we see an example of another type of lipid. We see an example of a triglyceride. A triglyceride is made up of a glycerol and 3 fatty acids. Yes, 3 fatty acids. So remember, fatty acid, it has a carboxyl group here, carboxyl group, and a methyl at the opposite end. Yes, so a triglyceride, you will have a glycerol plus these 3 fatty acids, giving us a triglyceride. Here, do we see any double bonds? No. So this is a saturated fatty acid. Do we see any double bonds here? No. Do we see double bonds here? Yes. So this is an unsaturated fatty acid. Alright, so this plus this will come together to give us B, and B is an example of a triglyceride. And here what do we see here as a byproduct of water? So what reaction is that? This is a dehydration synthesis reaction. When it comes to our fatty acids, we can get them from our diet, but some of them are essential, which means our body cannot make it themselves. We need to get them in our diet. Those are our omega-6 and our omega-3 fatty acids. Next, we have some more lipids. We have our triglycerides, like we mentioned. It is made up of 1 glycerol and 3 fatty acids. They come together through a dehydration synthesis reaction. The functions of our triglycerides is energy storage, thermal insulation, and shock absorption of our vital organs when stored in our adipose tissues. This little information just goes through the difference between an oil and a fat. I want us to just know what a triglyceride is, and when studying, you can go through the differences between the oils and the fats. Next, we have our phospholipids. Our phospholipids, they are major components of what? Hopefully, we're all yelling of our cell membrane or our plasma membrane. Your phospholipids are similar to our triglycerides, but they have one of the three fatty acids is replaced by a phosphate group. All right? And your phospholipids, they are amphipathic, which means they have both hydrophobic and hydrophilic regions. The tails are the hydrophobic regions, and the phosphate heads make it hydrophilic. All right, so this is the representation of lecithin, which is a representative phospholipid. The glycerol group here, the phosphate group, and the nitrogen containing group here. Hydrophilic, hydrophobic tails. Next, we have eicosanoids. Eicosanoids are a group of bioactive lipids derived from fatty acid, derived from the fatty acid arachidonic acid. They function primarily as hormone-like chemical signals. Usually, it is through paracrine functions. They have many different functions. They can function as, for example, prostaglandins are a type of eicosanoid, triboxanes, leukotrienes, so many different types of hormone-like functions performed by our eicosanoids. And next we have our steroids. Steroids are lipids characterized by a core structure of 17 carbon atoms arranged in 4 rings. You see here 1, 2, 3, 4. And the most important steroid is cholesterol. It serves as a precursor for all of our steroids. Steroid hormones like cortisol, progesterone, estrogen, testosterone, and bile acids. So yes, cholesterol has a reputation for contributing to cardiovascular disease when present in excess. So a lot of cholesterol is bad for you, but our body still needs it. It needs it, for example, for cell membrane function to make all of these other hormones. Most cholesterol in the body is synthesized internally, primarily by the liver, with only a small source coming from dietary sources. So technically, we do not need to have a lot of cholesterol in our diet. Our body is able to synthesize it. So we do need to limit it in our diet, but our body still needs cholesterol. It's a lovely table from your book going through some of our lipid functions. I want us to know, of course, that bile acids made up of cholesterol. We see here some fat-soluble vitamins A, D, E, and K. These are our fat-soluble vitamins. You need to know that, and the rest of these you went through in the previous slides. Next, we have our proteins. A protein is a polymer of amino acids. An amino acid is, in the name, it tells you what it is made up of. It has a central carbon with an amino group, a carboxyl group, and then a radical group, the R group. So here we see 3 examples of amino acids. All of them have a central carbon with an amino group, a carboxyl group, and a hydrogen, and then in pink highlighted is the radical group. We have 20 amino acids used to make our proteins, and they're all identical except for the radical group. And the properties of each amino acid is determined by that R or radical group. If we have 2 amino acids coming together, they will form a bond called a peptide bond. A peptide bond is actually what helps the formation of this peptide bond is a dehydration synthesis reaction. If we have 2 amino acids forming a peptide bond, we call that a dipeptide. 3 amino acids, tripeptides. 3 to 15, oligopeptides. 15 to 50, polypeptides, and more than 50, that is then now called a protein. So here we see the formation of a peptide bond, the hydroxyl group of one amino acid and the hydrogen of the amino group of another amino acid coming together to a dehydration synthesis reaction, giving us a peptide bond and water. Our proteins have a specific three-dimensional shape. That means it has a specific conformation. And this three-dimensional shape is crucial for that enzyme to function properly. If the shape is not correct, the enzyme or that protein will not function correct at all. Proteins can reversibly change conformation to affect their function. So if we need to have muscle contraction, we will change conformation. If we need to stop contraction, we'll change conformation again. Proteins can also undergo denaturation. So this is extreme conformational change that destroys function. So say maybe there's extreme heat or pH change. Now my protein will now have irreversibly changed its shape. It will have irreversibly changed its three-dimensional shape and structure. That is now called denaturation, and will not be able to function properly anymore. A very extreme example of this is when you cook an egg. A cooked egg white becomes opaque and stiff. Can you get it white? Can you get it back to that white, the yellowish, clear egg white? No, you cannot. It cannot revert back. It is permanently and forever changed. When it comes to our proteins, we have 4 levels of protein structures. If we just have a linear sequence of amino acids, and each amino acid is bound by a peptide bond, so we have amino acid, peptide bond, amino acid, peptide bond, amino acid, peptide bond. That is called the primary structure of a protein. From primary structure, we can then go to secondary structure. This is now where we have, because of hydrogen bonds between the carboxyl group and the amino groups, we can now form hydrogen bonds. We can either form hydrogen bonds that form a alpha helix or a beta pleated sheet. So whenever you see an alpha helix or a beta pleated sheet, that is the secondary structure of a protein. And what holds that structure together? Hydrogen bonds. Next, we have the tertiary structure. The tertiary structure is folding and coiling due to the interactions of the radical groups and between among the radical groups and between the radical groups and the surrounding water. So now we have the R groups interacting with each other and within themselves and with the surrounding water, giving us the tertiary structure. And then next we have quaternary structure. This is now the association of 2 or more polypeptide chains with each other. The example of this is the structure of hemoglobin. Here's what we see here, where we have 4 polypeptide chains interacting with each other, giving us the structured hemoglobin. Alright, we have 2 or more polypeptide chains interacting with each other. Linear amino acid peptide bonds, primary. Alpha helix or beta sheet and hydrogen bonds, secondary. R groups interacting within and with each other and surrounding water, tertiary. Polypeptide chains interacting with each other, quaternary. Yes, we need to know this very well. The different functions of our proteins, I'm not going to read through this slide, but you need to know the different functions our proteins have. So say I were to ask you, what function of protein says that it holds your proteins together, helps with fertilization, immune response? You would say cell adhesion. If I say what structure of proteins, what protein function helps it function as an enzyme, involved in metabolism, digestion, you would say that is catalysis. So know your major functions of our proteins. We have structural support, communication, like your receptors, membrane transport, like your protein, like your sodium potassium pumps, catalysis, your enzymes, most of your enzymes are proteins. recognition and protection, movement, so your motor proteins like myosin, and cell adhesion. Enzymes and metabolism. So enzymes are proteins that function as biological catalysts. How do they do so? By lowering the activation energy, which is the energy needed to get a reaction started. It permits reactions to occur rapidly at body temperature. So at body temperature. And when we have these enzymes, we also have substrates. A substrate is a substance an enzyme acts upon. And enzyme naming, it will often have the suffix ase. So you also amylase, lactase. Yes, if you see that ase at the end, it is most likely an enzyme. So here we have an example of the enzyme and the substrate. When the enzyme and the substrate interact, they form an enzyme-substrate complex. We will then also utilize water to break that bond. What reaction is that? Awesome, I heard it. Please know what reaction that is, giving us our two products. And here we see how our enzymes lower the activation energy, which is the energy needed to get a reaction started. Without the enzyme, and here we have with the enzyme, you're lowering the activation energy. And the same example again, but here now we have the specific example of the substrate sucrose and the enzyme sucrase, enzyme substrate complex here, and then we have our two products, glucose and fructose. Are you seeing here that the enzyme is not being used up? The enzyme it catalyzes the reaction, but itself is not being used up, so we can go through this reaction over and over and over again. So that's what we see here. Enzymes are not consumed by the reactions. One enzyme molecule can catalyze millions of reactions per minute. Temperature, pH, and other factors can change enzyme shape and function. What is that called again? Changing its conformation, yes. And it can alter the ability of the enzyme to bind to the substrate. Alright, so enzymes vary in optimum pH. For example, salivary amylase works best at a pH of 7, but pepsin in the stomach works best at a very acidic pH of 2.0. We also have cofactors. Cofactors are non-protein helper molecules whose presence is necessary for many enzymes to function. So we have cofactors. Some cofactors are inorganic molecules like copper, zinc, magnesium, and some cofactors work by binding to the enzyme and triggering a conformational change that activates the active site. So those are cofactors. We also have coenzymes, which are organic cofactors. These are often derived from vitamins. So here we have the cofactor NAD, derived from the vitamin niacin. It plays an important role when it comes to metabolism and ATP production. And next we have the fourth organic molecule we're going to look at, organic compound we're going to look at, which are our nucleotides and our nucleic acids. A nucleotide is an organic compound with three principal components: a nitrogenous base, which could be a single or double carbon ring, a sugar, and one or more phosphate groups. So a nucleotide will have a nitrogenous base, it will have a sugar, and it will have one or more phosphate groups. Some examples of our nucleotides are ATP, a very important compound here, adenosine triphosphate ATP. It is the body's most important energy transfer molecule. We also have GTP, guanosine triphosphate, another nucleotide involved in energy transfer. Another important one we see here. So this one here is actually adenosine triphosphate, where we have adenine, ribose, and 3 phosphate groups. Here we have cyclic AMP, where we have ribose and adenine and only 1 phosphate group. Cyclic AMP, cyclic adenosine monophosphate, is formed by the removal of the second and the third phosphate groups of ATP. It's the formation triggered by hormones binding to the cell surface, and cyclic AMP becomes our second messenger within the cell. So cyclic AMP is a very, very, very important second messenger. Nucleic acids are polymers of nucleotides. So when you have a nucleotide plus a nucleotide, you will have your nucleic acid. Some examples of nucleic acids are DNA and RNA. DNA stands for deoxyribonucleic acid. This is your DNA, what is found in the nucleus of your cells. It constitutes of genes, and your genes have instructions for synthesizing proteins. So your DNA is a nucleic acid. RNA, because ribonucleic acid, is also a nucleic acid, and we have 3 types of RNA: mRNA, which is messenger RNA, ribosomal RNA, and transfer RNA. It is much smaller than DNA, and it carries out genetic instruction for synthesizing proteins as well. It assembles amino acids in the right order to produce proteins. So DNA and RNA are examples of nucleic acids. And what are nucleic acids? Polymers of nucleotides. Here I have the example of ATP again. That's how important adenosine triphosphate is. Adenosine triphosphate is associated with enzymes called adenosine triphosphatases, ATPases. They are specialized to hydrolyze the 3rd phosphate group, producing adenosine diphosphate and inorganic phosphate, and when it does so, it also helps release energy. Yes, it helps us get our energy. So most of this energy escapes as heat, but we live on the portion of it that does useful work. So the free phosphate group released by ATP hydrolysis is often added to enzymes and other molecules to activate them. And when we add a phosphate group to an enzyme or a protein, we call that phosphorylation. And this phosphorylation is carried out by enzyme called kinases. The phosphorylation of an enzyme is sometimes the switch that turns a metabolic pathway on or off. So these all work together. So ATPases gives us those inorganic phosphates. Kinases that use those phosphates to undergo phosphorylation, where they add phosphate group to other enzymes, turning those enzymes on or off. And that was chapter 2. Here you have the end of chapter questions, and I noted the important ones, which is all of them. Please test yourself by going through them. The answers are here. And then I have a couple of practice questions for you to go through. Please really try to get to these answers, to answer these questions. Very important questions here as well. And that is chapter 2. Thank you so much.